You want to test the claim that the average number of words a child knows when they start first grade is greater than 131 words. You administer a test to 28 children starting first grade and record the results. If alpha, our significance level, equals 0.025, find the critical value to 3 decimal places. So the first thing I want to do is figure out what kind of test, left, right, or two-tail, this is. And the way I'm going to do that is, first I will make note of my claim. In symbols, the claim is that the average number of words a child knows when they start first grade is greater than 131. So mean is greater than 131. Now I want to do the opposite of that claim, and the opposite of greater than is less than or equal to. The equal to tells me this is going to be my null hypothesis. So I'm going to change that to equals. So mean equals 131. And that means this claim is what corresponds to my alternative hypothesis. And the alternative hypothesis, that tells me this is a right tail test. The greater than tells me it's a right tail test. So that means I'm going to put that area of my significance level all into the right tail. So now I am looking for the critical value down here that has 0.025 to the right. Well, can do this two ways. I can look at our t distribution table or use some technology, and I'll use a spreadsheet. So first of all, if I'm going to look at the distribution table, I need to know two things. I need to know the significance level, I guess maybe three things: the significance level, the fact that it's a right tail test, and the number of people in this test. Really, I need the degrees of freedom, and we are always using degrees of freedom as n minus 1, which would be 28, the number of children in our study. Minus 1 will leave me with 27. So that means my critical value must be somewhere down in the 27th row. That's my degrees of freedom. And my significance level is 0.025. Now it's important to realize that this is a right tail test, so we don't look in the area in two tails, we look in the area in one tail, 0.025. So I look in the middle column in the 27th row, and my critical value is then 2.052. Now one thing to note, if this had been a left tail test, the same process applies, we just turn this into a negative 2.052. Now, if I want to use a spreadsheet, I'm going to use the t.inv formula. And the probability is 0.025. The degrees of freedom we found is 27. Now that gets me a critical value of negative 2.052 if we round it. So what that formula does is it gets me the critical value that has 0.025 to the left. So I could do one of two things. I could either say I know this is a right tail test, so I make that positive, or I could subtract my significance level from 1, and that means I would be plugging in 0.975 for my area in the tinv function, and now it'll give me the positive. Probably easier just to plug in your significance level and know whether it's a left tail or a right tail. If it's a left tail test, you're going to take the negative critical value. If it's a right tail test, you're going to take the positive. If it's a two-tail test, then what you're going to do is find the critical value by plugging into tinv. So let's say this example was a two-tail test. If I plug in 0.025, I get this answer. However, if I divide this by 2, that's how I can get the critical value for a two-tail test. So dividing my 0.025 significance level into 2, I would plug in 0.0125 for my area. And now, because it's a two-tail test, I would have both the negative and the positive critical value. But that's for a two-tail test. For us, we have a one-tail test, so I'm just plugging in the area, and then because it's a right-tail test, I'm going to take the positive value.